but it allows you to get a quantitative handle on a lot of processes that you'll have a hard time figuring out otherwise. I once made myself unpleasant in ninth grade math by asking if it was possible that the rule of 72 could be false. If there could be a possible world and a possible system of mathematics in which it wasn't true. I think the answer was no, that this is something that is inscribed in the nature not just of our realities, but of all possible realities. So a little bit more complicated. Suppose we have a process growing at 4% per year. How long is it going to take it to octuple? How long is it going to take until it's 8 times as big as it started out as? Okay, closing in on the wire. Bingo. Okay, yep, C is the right answer. You have a good plurality at C. The way to think about it is if its growth is octuple, if it's an octupling, that means it's doubling 3 times. It doubles, and then it doubles, and then it doubles again. That gets you from 1 to 2 to 4 to 8. Doubling 3 times, each doubling takes 18 years. An octupling will take 54 years, will take the time of 3 doublings. That's what I want you to know about compound interest and about cumulative process. Now let's turn to the basics of our model. As we said, we were going to worry about real GDP, Y, and its determinants. And its determinants were going to be resources and technology. And for resources, we'll think about the labor force, which we'll call L, and the capital stock of machines and buildings in the economy, which we'll call K for capital. Why not C? Because we'd already decided to use C for consumption when we got to this. And at least capital begins with the letter K in German, so that's something. It's not a great notation system, but we're stuck with it. And for the efficiency of labor, we're going to use the letter capital E, E for efficiency. And we're going to start with a production function. We're going to write down a simple algebraic mathematical rule relating what the real GDP of an economy is going to be as a function of its capital stock, of the efficiency of the labor force, and also of this little Greek alpha thing, the script A, which is going to tell us something about the relationship between capital accumulation on the one hand and increasing productive potential on the other. We're also going to want to think a lot about the capital output ratio in the economy. That is, take the value of all of the machines and buildings of all the capital in the economy and divide it by a year's GDP. And so the capital output ratio, K over Y, we'll write that by this little script lowercase k that's actually a Greek lowercase kappa on your keyboards. We're going to think a bunch about the determinants of that kappa as a way of getting to what the level of output is going to be. So why this function? Why write down this rule that Y equals the K to the alpha times paren EL close paren to the 1 minus alpha? Or more English, that an economy's level of real GDP can be determined by taking its capital stock and then raising its capital stock to the algebraic power of some number alpha between 0 and 1, and then multiplying that by the product of the efficiency of labor and the size of the labor force in the economy, also raised to an exponential power, but in this case the power 1 minus alpha. It's not the case that there's an enormous machine buried somewhere in the earth called the production function that determines what the level of production in an economy is going to be. You know, like one of those science fiction novels in which the machine takes over people's brains and it calculates what they're going to do, and so it makes them perform the amount of work that produces that amount of final output. No, instead people have work with their machines and their buildings, and they make stuff, and they sell stuff, and they trade stuff, and they buy intermediate goods, and they sell intermediate products, and the whole thing adds up, and you have your final sales, and that's the GDPY that's measured, and the Bureau of Labor Statistics counts the labor force, and the Census of Manufacturers and other censuses try to count the capital stock. And it all adds up in a huge mishmash of 150 million workers, 10 million firms, uncountable items of technology, uncountable numbers of capital, $14.2 trillion of GDP. Why are we pretending that we're going to analyze the economy as if there's this gigantic algebraic machine sitting under the earth somewhere, and we simply feed it 4 numbers, and it cranks for a while and comes out with a number for real GDP? Well, we want to write down this algebraic relationship because we hope it's going to be a reasonable approximation to how the real world works in a certain sense. In what sense? Well, we think that if we were going to double the labor and capital in America, we'd probably double the level of real GDP. That for every factory before, we'd have 2 factories after. For every worker before, we'd have 2 workers afterwards. Twice the number of workers working with twice as many machines and twice as many buildings. It's hard to see why that wouldn't produce twice as much output. So if we're going to write down a very simple rule to kind of tell us how production varies with the resources the economy has, it better be one in which if we double resources, we double production. And this algebraic function has that property. We also would like it to have diminishing returns. That is, back in the 1950s, I think it was IBM President Thomas Watson said that he thought there might be a demand for 5 computers in the world. One of them would be for the United States' air defense system. One of them would be for the Soviet Union's air defense system. There'd be another one that the Census Bureau would need to do its calculations. Maybe the biggest insurance companies would want to have one. That's how we got up to 5. Everything else, he said, paper and pencil and mechanical calculators should be enough. But the computers that were in use then were all extraordinarily valuable. People really, really loved them. They were scheduled within an inch of your life. Even in the mid-1980s, back before most of you were born, when I was working with computers, the time of the computers was so scarce that we economics graduate students were only allowed on after 5 p.m., after the more high-priority users had gone home. And furthermore, unless our programs were absolutely perfect, it was simply not worth the time of the central processing unit to spend any time running it. So we would take our large decks of punched cards, one after the other, over to the computer lab, and we would feed them into the computer card reader. And almost all of the time, what would come back would be that the preprocessor saw your program and it was incoherent. Job control language error in statement 6. Go back and punch another card and swap in the good card for the incoherent card, and then we'll let you submit it again in another 2 or 3 hours when the job submitted by people who understand how to do computer syntax actually run. This meant that being a research assistant for an economics professor in the mid-1980s was an extremely cushy job because you would basically work for maybe 5 minutes an hour trying to fix your programming errors, and then you have to wait for 55 minutes for the job to come back and tell you what your errors were. Right now I have 1, 2, this has 2, 4, this has a 5th, this has 2 more, Right now, I'm using 7 microprocessors, each of which is more powerful than all the computers in the world were in 1955. Yet the value produced by the computers in the world in 1955 far exceeded the value of my 7 microprocessors, which are at the moment doing nothing other than substituting for this particular transparency projector, and letting me put a slide up on the screen. If you have more capital in the economy, if you double the amount of capital in the economy without doubling the amount of labor, you do not expect to double the amount of output. Instead, output is going to go up by some smaller amount. So you'd like to have a rule for describing how production relates to resources, by which if you increase the economy's capital stock by 1%, you don't increase production by 1%. You increase production by something less than 1%. By how much do you increase production? Well, that's what this letter alpha is supposed to tell you. Alpha is going to be some number. Alpha is going to tell you how quickly these diminishing returns to investment and capital accumulation fit in. If alpha is small, if alpha is near 0, then you increase the capital stock and you don't increase production by very much. Diminishing returns set in immediately. If alpha is almost 1, well, you increase the capital stock by 1% and production increases by almost 1%. Diminishing returns take a long time to set in. The reason we like to write down this particular function is it allows us to tune itself across a number of different economies. Have an economy in which diminishing returns set in quickly, then you can use this equation and just say that alpha is going to be something small near 0. Have an economy in which returns aren't diminishing very quickly at all, well then use this equation and say that alpha is close to 1. So we insist that you want to double labor and capital and you're going to double production. We insist that if you want a model that will tell us if you increase the economy's capital stock by k%, you're going to increase output by some lesser number by alpha percent. And you also want to say that if the labor force is constant in the economy and if the capital output ratio is constant, if you're kind of saving the same proportion of output so that output bears the same relationship to capital as it used to, and if the efficiency of labor grows by 1%, then you'd like output and the capital stock to grow by 1% as well. You'd like that to be true, and that's largely a matter of definition. That is, if the capital stock grows by 1% and the efficiency of labor grows by 1%, you really would want output to grow by 1% too, and if it doesn't, then you have the wrong definition for how efficiently you're using your labor. Those 3 things, constant returns to scale, diminishing returns to investment in capital, and this definitional thing that the efficiency of labor in this equation should actually measure the efficiency with which labor is used to produce things, those 3 things nail this function down. This is the only rule that you can write down relating labor, capital, the efficiency of labor, and this diminishing returns parameter alpha, and get output out as a result. So we really don't have much of a choice if we want all of those things to apply, and also get an equation that's extremely easy to use for what-ifs, and also give you an equation that's flexible. So from now on, we're going to ruthlessly simplify all of our 150 million workers and our 10 million firms and so forth down and simply say that the market economy is going to take the labor, the capital, the efficiency through the technology, through efficiency of labor that we throw at it, and it's going to tell us what the level of real GDP is. It's going to be Y determined by this equation. So that's the first part of our model. It's going to be this production function. The second part of our model is going to say that we're going to want to study economies that are in some sort of balanced growth, that we're not going to be terribly interested in situations in which the capital stock in an economy is growing much faster than production, or in which the capital stock is growing much slower than production. Why not? Well, because such situations are unstable and transitory. That, after all, if the economy is saving a large share of its output, then the capital stock K will be growing faster than output, and the capital output ratio will rise. And as the capital output ratio rises, diminishing returns will set in, and each additional unit of capital is not as productive, and so our ability to keep the capital stock from growing as fast will slow down. And eventually, the economy will converge to a point at which it's saving just the right amount, where the capital stock and the output level will be growing at the same rate, and thus our little script K, our capital output ratio will be constant, and growth will be balanced. And this is another thing that economists do. The world is complicated and tends to be out of anything you might call of economic equilibrium at any point in time. But in general, the world is heading for, the economy is heading for some particular equilibrium configuration. And if the economy gets to that equilibrium configuration, it's going to stay there until something else happens to disturb it and shock it and knock it away. And it's a lot easier to analyze equilibrium configurations than dynamic disequilibrium ones. So we're going to focus first, and I think last too, on balanced growth equilibriums. Say that there was a time in the past when the economy was out of equilibrium, its growth equilibrium, when capital and output were growing at different rates. And maybe I'll make you do one of those on the second problem set. But for the most part, we're going to say we want to assume that whatever process has pushed the economy toward its equilibrium configuration has come to an end. And we just have to worry about situations in which the capital output ratio is constant, in which the economy's capital stock and its level of output are growing at the same rate. And then what is just the right amount when we say the economy has to be saving just the right share of production? Well, it's easy to figure out. The textbook goes through this in exhausting detail. The way it's simply a property of our particular production function. That after all, if the capital stock K goes up by 1%, then Y goes up by alpha percent. So if the efficiency of labor E goes up by G%, and L goes up by N%, and Y goes up by Y%, then we can write down this Y, little y equals alpha little k equation, where little k, lowercase k, is the amount by which the capital stock is going to go up. This is simply an immediate consequence of our writing down this particular production function. And if growth is to be balanced, then Y has got to equal k, little y has got to equal k, that the capital stock and the level of output have to be growing at the same rate. And that equation tell you immediately that the rate of growth of output, little y, is then going to be the rate of population growth, n for number of workers, plus this thing g, and g for growth, the growth rate of the efficiency of labor. So what did I just say that the n in our model is in this equation y equals n plus g? Immediate retention question. Important from my perspective to figure out how much setup I have to try to give these things for the lectures to be truly worthwhile. Not just for me, right? I seem to get paid whether I lecture well or badly, but more important for you all. Only 46%, the rate at which, the rate of growth of population in the labor force. The rate of growth of the efficiency of labor, that's going to be capital E in this model. The number, or rather the value of capital goods in the economy, that's going to be capital K in our economy. The share of GDP that's saved and invested, that is devoted not to consumption either by the government or by household, but instead to saved and invested to add to the economy's capital stock, that's going to be S. The steady state level of population, That's in one of Thomas Robert Malthus's models of stagnation and despair. We aren't going to be doing that, at least not right now. Right now, n in our model is the rate of growth of the population and the labor force. And the important thing to carry away from reading the textbook is that in balanced growth, the rate of growth y of the economy, of real GDP in the economy, is going to be equal to the rate of population growth n plus the rate of growth g of the efficiency of labor. Another question as to whether this is getting in or not. When we write our production function, the point of the little L script alpha is what? Is it the rate of increase of the efficiency of labor? Is it usually less than 0.5? Is it always greater than 1? Is it the rate of growth of the capital stock? Is it a number that determines how rapidly returns to adding more capital to the economy diminish? Okay, we have 2/3. Yep, okay, people are converging in. That's not fast enough. Yeah, it's the number that tells you how rapidly returns to adding more capital to the economy diminish. That's the function of alpha. If alpha is small, near 0, then there's really not that much point in trying to tune the economy to save and invest more. If alpha is large, near 1, then there's a lot of point to saying we should be saving and investing and accumulating more and adding more to our capital stock. Although I dare say with at least some kinds of capital equipment, we seem to have reached near satiation. That is, I can't figure out how having an 8th working microprocessor at my disposal right now would raise my productivity at all. Now, like I said, maybe if this thing had another core, it could do a better job of indexing the hard disk. But that's extremely low value. Now, let's skip this one. You've already asked more than enough. Okay, so we had our steady state balanced growth equation. We said that if growth was to be balanced, that y, the rate of growth of output, had to be equal k, little k, the rate of growth of capital. And so the rate of growth of the capital stock, little k, has to be equal to little y, the rate of growth of output, has to be equal to n, the rate of growth of the labor force, plus g, the rate of growth of the efficiency of labor. But we also want to say something else about the rate of growth of the capital stock. We want to say that every year a fraction delta, this little d with the script tail, in there, capital wears out, becomes obsolete, rusts away, breaks, has to be replaced. So that if nothing else were going on, the rate of growth of our capital stock would be negative as the stuff wore out. But we don't just have depreciation. We also have savings and investment. We take a share S of our total GDP and we save and invest it in adding to our capital stock. How much does this savings increase the capital stock? Well, to figure out that, we have to take S and we have to divide it by the capital output ratio kappa. If the capital output ratio is very low, then a given share of output saved will produce a huge increase in the capital stock in relative terms. If the capital output ratio is very high, then even a big amount of savings S will produce only a small increase, relatively speaking, in the capital stock. We capture this by dividing the savings rate by the capital output ratio. And so now we have two equations for what the rate of growth of the capital stock has to be if the economy's growth is going to be balanced. On the one hand, we know that the rate of growth of the capital stock is this S over kappa minus delta, this term that comes from the combination of savings to add to the capital stock on the one hand and depreciation to reduce it on the other. On the other hand, we know that output's going to be growing at n plus g, and that the capital stock, if the economy's balanced, has to be growing at the same rate. This gives us S over kappa minus delta equals n plus g. And that tells us that the economy's capital output ratio, well, in order to calculate what the economy's capital output ratio, you simply take its savings rate and you divide it by the sum of three things. Of delta, the rate at which capital stock wears out, the share of capital in the economy that wears out every year. G, the rate of growth of the efficiency of labor as you add more and better technology to your workers' skill sets. And N, the rate of growth of the population in the economy. So now we've managed to nail down, if our economy is balanced, just what its capital intensity will be, of how much capital there'll be for every unit of annual output. That's an important thing to nail it down, because then we can start calculating what the level of output in the economy is going to be. And we should start with our production function. And since we know what the capital output ratio is going to be, why don't we take the capital stock K and replace it by something that involves the capital output ratio? Well, capital is simply equal to the capital output ratio times the amount of output. That's an identity. You can then distribute the exponent in order to get all of the y and the little kappa terms by themselves. You can then divide in order to get all your y terms on the left. You could then exponentiate to get y by itself on the left. And so you get that output is going to be equal to the efficiency of labor E times the labor force L, and then times this term in front that's missing a parenthesis. There should be two parentheses after the second alpha. But that is the capital intensity of the economy, the capital output ratio, raised to this peculiar power, to this alpha divided by 1 minus alpha power. Well, we know what the capital output ratio is going to be. We know what the capital intensity of the economy is. That's why we went through all of these calculations here to get the capital output ratio as S over N plus G plus delta. And so we can then simply substitute in for output and for output per worker and get nice little relatively simple expressions for how output and output per worker depend on the efficiency of labor, on this alpha diminishing return stuff, and on our four behavioral variables.